Yeah. Good morning. Good morning, everyone. So I just want to take a few minutes to actually see the spirit of this whole workshop and what is that I would like to present and how you can benefit from these lectures. First of all, no, it's very, yeah. All right. Yeah, so thank you, Professor Sai Prakash, for inviting me, and thank you for the institution, the NIT Warangal, to host this program. As I said in the inaugural session, I had the privilege of actually learning the subject over the past 12 years or so. Then I was able to also engage in a practical setting, in a real world application, under the supervision of NASA and several industry partners. So the key things for learning, and appreciating a subject, any topic, in not only engineering or anything that you want to learn, it requires three components, in my opinion. One is reading. You read from the books, from the textbooks, and of course, teachers are like, as our tradition says, there are gurus. They will impart that wisdom more than what you read in the book. You learn from the teachers. I think there was some discussion before. You can learn a lot of things on YouTube and all those things, but nothing compares to learning from a teacher's face, teacher's own words, and being present in the classroom and learning from the teacher is the best thing, the best way to learn. The third thing is, okay, you learn something, then what? Then the second stage. Second stage is you contemplate on it. You do your own research in your own mind, how things work. For example, if you say V equal to U plus AT, then yeah, that's a nice equation, fine. Then you understand, what is V, what is U, what is A, what is T, and then you figure out, or maybe you do some experiments on your own and say, okay, yeah, this makes sense. Velocity equal to initial velocity times plus acceleration some time. So you see the role of each of those variables. So this is your own investigation, your own mulling over, your own thinking process or analysis, and then starts your real learning. You want to engage in something. For example, maybe you build a toy vehicle, and say whether this V equal to U plus AT actually makes sense. So that's where you really start appreciating the topic. So basically, the three components are reading, learning from a teacher, then doing your own research, and then having the experience of it. If you don't have, without experience, is not complete. So what happened in my case is, sometime around 2012, I think, the real work started about drones. Drones have been there in the military world, but not in the civilian side. Nobody expected today that drones will be delivering a salt packet. This is I live in Frisco, in Dallas-Fort Worth suburb. So what's happening there is, based on the past research and development work that started in 2014. I'll give you a snippet of how things worked out. 2014, NASA started a project called UTM. UTM stands for UAS traffic management. But so UAS means drone. We call them drones, we call UAVs, unmanned aerial vehicles, and a system of UAV plus all other accessories is called UAS, unmanned aircraft system. So the research started in the research and development, not just research. It started in 2014, and NASA worked with several what we call centers for excellence, specifically dedicated for drone research. So it worked with those centers for excellence, and it worked with industry, many companies, and together they came up with a scheme, an overall framework for drone deliveries. And fast forward 10 years, 2024, sometime in October, November, December last year, drone deliveries started happening. Literally, during the Valentine's Day on February 14th, I don't know why they picked that day, Walmart said, we are going to deliver Frito-Lay's those chips to everybody in Frisco. So the point is, what started as a research project in 2014, 10 years, it turned into a real world application. It's unimaginable. And how does that, what is the life cycle in this 10 years, what exactly happened? People like you and me, started working with drones and see what does it take to fly a drone or make the drone autonomously fly from point A to point B, like toys, with building some toys. Literally that's what happened in 2008 when I joined my university. Some students said, oh, we want to build a drone, can you be our mentor? See, remember, teacher doesn't know everything ahead. Sometimes we do research together. Many of the research scholars agree with this, that the professor and the research scholar investigate the things together. So here, the undergrad student wanted to build a nice drone, and then we were guiding them. I was guiding them, but ultimately it is the student who actually built the drone. And then in 2014, when the UTM started, it's like I was fortunate enough. One of the centers for excellence in Corpus Christi, they called me and said, "Can you help us with drone-to-drone communications?" So once again, it's the beginning of drone-to-drone communications work for me. So I ordered some radios. Those radios are same radios that were used by cars. It's called DSRC. I put those radios on the drone. So we flew 2 drones, and there is a what you call a ground control station, and 2 drones were flying. So we have 3 radios, one on the ground and one each on the 2 drones. So we actually tried how far these communications can go between the 2 drones. And then before that, something more fascinating happened. Remember this, around that time, 2014, 2013, there was this Malaysian aircraft. The year may be wrong, just I don't remember exactly, but there was a Malaysian aircraft crash. Then we didn't know where it was. So one of the problems is lack of global tracking, meaning that when the drone, when the vehicle, aircraft crashed, we didn't know where it was, because it's not even being tracked. So the outcome of that is the investigation is that every aircraft should have some sort of a device. Like now it became called ADS-B. ADS-B is like a transponder that aircraft is going to tell its location, and the ground stations can track. So those are that's the outcome of this. For a drone, there is something similar. It's called remote ID. Remote ID is a small device, and now if you look, it's a very small footprint that goes onto a drone, and the drone actually tells every second, or maybe more than at certain frequency, the drone will tell where it is located. So with that remote ID, we can identify where the drone is. It's specifically for law enforcement agencies, but it's good to use for other purposes also. So the point is, this evolution finally ended up with a full-blown drone delivery service in 2014. And the same way, around 2018, to be very specific, 2018 November, NASA started a program called Urban Air Mobility. The Urban Air Mobility turned into Advanced Air Mobility, and they changed the name to some other name called AMP. So it started in 2018. Effectively, from 2020, the real research and development work started. And fortunately, I was able to engage in this project. So what do you mean by engaging? I work with the industry while the NASA and the Federal Aviation Administration were supervising the project. We did a lot of simulations in 2022, and ultimately I was leading this group of industry. We call that the North Texas cohort, that demonstrated the very first experiment on advanced air mobility, a vehicle flying at a height of 11,000 feet for about 30 miles, and we tested some features of autonomy. So that was the kind of a very first experiment in Texas for sure, probably third or fourth in the whole country. And I'll show you some articles that were published. So that advanced air mobility project was started in 2020. I think by 2030, this is everybody is guessing, including also my guess. We see some reports that expecting that by 2030, you are going to see advanced air mobility in real life. So there is a difference between the previous project that I talked, UTM, and this project is called advanced air mobility. The difference is UTM is for drone deliveries. So these are small drones flying about 400 feet, roughly 1 meter equal to 3 feet. So you can say about 400 by 3, about 120 meters or so. And then advanced air mobility vehicles are large vehicles carrying people. So it's like you can call unmanned air taxi. More correct term is uncrewed air taxi. There is no reason for just saying unmanned. So it is an uncrewed aircraft carrying people from place to place. There are challenges, of course. So notice the difference. When I say drones, they are small drones flying at about 400 feet. And when we talk about air taxis, they are flying about 10 times that, 4,000 feet, or about 1,200 meters and above. Okay. So these are not exact altitudes, by the way. 400 feet is something normal, but as far as air taxis are concerned, actual altitude will be determined by the Federal Aviation Organization. And one more interesting fact is, who manages the traffic for drones and air taxis? It's not the government, it's not the Federal Aviation, it is a private industry. So there are things might change over the time, but primarily, even though the guidance and supervision and overseeing the projects are done by government, practically drone deliveries and air taxis, all this are going to be managed by the industry. Anyway, so what I'm trying to draw a comparison is what started in 2014 as a research and development program by NASA turned into real world application in 2024. The same way, the expectation is what started as a research and development project in 2018, it picked up around 2020. By 2030, we expect air taxis to be prevalent. Okay? And of course, success depends on many factors. It's not just technology. How well the community accepts this. So air taxis are not just technical development, technology development. It depends on community acceptance. So we'll talk about all this. So my experience is that I engaged in both the UTM project as well as AIM project, and that is why I am so passionate about this subject. So when Dr. Sai Prakash invited me to give this workshop, I was so happy because everything that I learned over the last 15-20 years, I'm going to share with you the principles, the fundamentals, plus the research, what kind of research topics are there for us to explore, and then the practicality of it. So this is what I want to share. My goal is by end of this 10 days, you pick one topic depending on your interest, and then I'll be more than happy to work with you. And of course, NIT has so many labs, so many facilities, and we're all so fortunate. I'm sure those people coming from other universities also, institutions, you have all those facilities. Depending on what facilities you have or what facilities you have access to, your own interest, your own passion, and I hope that you take one topic and go deeper, dive deep into the subject and learn whatever you can, demonstrate what you can do, and then share this knowledge back to the world. Okay, that is my aspiration. So let me start with our first lecture is deployable aerial communication networks. So the way I want to present these lectures is I'm going to give you a broader picture, the broad picture, okay, and then tell you what I have done, what I learned, and then we'll pick one topic, one specific research topic. So for example, if you are a very meticulous person, you don't, even though of course the big picture you need to know, but at the end of the day you may want to pursue just one topic for your thesis. I want to make sure that you take away something from this class. Okay? Now, for example, let's talk about deployable aerial communication. Why this is so passionate to me is that about 2016, I think, and I was thinking, first to begin with on my own, that okay, can we put a communication system on a drone and deploy it so that you can when something happens like a disaster, earthquake or something, can we use this to provide instant communication? In fact, even at that time, my vision was that there should be such facilities, such infrastructure should be available at every fire station, for example, or every police station. So when something happens, just deploy the drone in probably less than 20, 30 minutes, and then make sure that the phones start working. And obviously, when you have an idea, you have to make sure, you have to remember that a lot of people will be thinking some similar ideas. Okay? No idea, unless you, at some point, of course, with all the knowledge and experience, you will come up with a novel idea that nobody has done. But in my lifetime, everything that you think, you can for sure think about there is somebody else who has done that. Okay? So, but what's fascinating is that I always first think about an idea on my own. This is what I suggest students also. Whenever some spark comes somewhere in your mind, just explore on your own. Forget about the rest. Forget about the world. Just explore on your own, and then see, and then come back to the literature and see, do the literature survey. So that way, you are not somewhat what I call influenced by the literature. Okay. So literature has both pros and cons. Literature helps you to learn what has been done before and what is new. But at the same time, if you think you come up with a new idea, I suggest that you explore on your own without looking at anything else, and then go and do the literature survey. So I tell that to my students. So this idea was, I started on my own, and then it was about 2014, 2015, I think I started this deployable communication, especially drone with a 4G communication system. That was the idea that I had. Then I reached out to many people. There was an association called National Public Safety Telecommunication Council. So I put an announcement there saying that, okay, I'm trying to do this experiment where I would like to airlift a communication system, like a base station, cell tower. Basically, it's called base station or cell tower. But we cannot say cell tower when you talk about airlifting, because there is no tower as such. So then somebody said, okay, we have a 4G system that is small enough that you can carry. So even before AT&T, right now AT&T has something called cells on wings. If you type, I'm going to show some pictures, and you can see on the internet also. But before they did, I did the very first experiment in Texas by engaging a startup company. That company is called, right now it's called Spectre Edge. They have a 5G base station now that is small enough to carry using a drone. So that article, that work was supported by the National Science Foundation, and when I submitted this idea, the program manager the NSF gave me $200,000, actually $213,000 for a couple of years. And then the same program manager actually funded me many times, because that partnership, even though National Science Foundation is a bigger organization, once you build a rapport with a program manager, they'll support you for longer time. So that program manager, his name is called Dr. David Corman. He has an aviation background, so he gave me the initial funding for $213,000. So we did work for 2 years and demonstrated the very first experiment, and I published that in IEEE Spectrum. It published in 2017. I'm going to show the link. And fast forward, last year, the same program manager gave me $1.5 million to extend that. I've been trying. It's not that suddenly we get successful. Over the last 10 years, I submitted 5 times. It was rejected. Because when you submit a proposal, peers like other researchers will actually review and then say what are the merits and demerits, and if everybody likes, then you get it funded. So this project was funded by the same program manager, and it was started in July last year to 2024. It is a 3-year project. Probably will be, I'll extend it for 4 years. And this time the goal is to put 2 base stations, 2 drones carrying 2 base stations, 1 each, and then to experiment with scalability, how far you can scale the coverage area. Now, we'll get into all those details. So that's the story of this project, this topic. Like this, each of the 10 lectures have some my own personal experience, not just research, not just fundamental ideas, but my own experience with the real world project. Okay, so that's why I'm so glad to share this with you. I think I might have started. So by the way, you can always ask me questions. In the middle if you want. Okay. Just a little bit. I think I shouldn't touch. Yes. So this is the outline. So we call that as a drone or a base station airlifted by a drone. We call that as a flying base station. I'll be careful enough not to touch all this. So we call that as a flying base station, or aerial base station. The difference is that normally you put a base station like 4G or 5G on the ground, and the tower is only to give you an altitude sufficient enough to give a line of sight. So not really that's the purpose of the tower. And then the catch here is you need to have the base station small enough to be able to airlift it. Plus, you also need, if you look at the architecture of a base station, you will see a radio node and then the core. So in the case of the experiment that we did, the company was able to put the core in a small, like a chip, like it's almost a credit card kind of a device size. So with that, we were able to put the whole thing as a payload, and that gives you some coverage, like an island of coverage for one base station. And these distances are not really big, depending on how much what you call the base station capabilities. The coverage is probably about 3 to 5, maximum 3 to 5 miles. So, but that is sufficient enough, especially for the people who are handling dealing with the emergency operations. We call them as first responders, like police and firemen. It is sufficient enough for them to be able to do the disaster relief operations. So at the end of the day, if you think of it, whenever there is a disaster of whatever scale, small scale or big scale, the first thing is power. You lose the power, and of course, if there is a magic way of what you call creating power instantly, that would be great. But since we are all, I mean, I'm a communication engineer, and we are also mostly in communications. The best thing that we could do is, can we restore the communication? So power is the first thing that goes up. Then is the communications. So, but by providing, by deploying, developing a deployable communication system, by establishing communications, you can save lives, obviously. So that is the intent of this project. So we will go through quickly, what do you mean by what a single ABS can do? One single aerial base station can do for us. And then my current project is about multiple ABSs. How can you scale? And I think this presentation was actually prepared by one of my students who is working on this project. So we did some survey, and the very reason the program manager actually gave me this project is to investigate scaling capabilities, because there is no such system that is in the market today. In the real world, one base station is deployed. For example, AT&T today has something called, as I said, cells on wings. All the demonstration that they did is only one flying base station at a time, only once. it will do its job, and probably the intent is to make sure that communication is established until the cell tower is repaired basically. So it serves the purpose, but it doesn't really serve the real purpose. The point here is that it's okay to fly once and then show that, okay, like for exercise, okay, your phones are working. That's not enough. In real world, there are many situations, whether it is a what you call the avalanche, ice storms that happened in recently in Uttarakhand, or there is a mud coming down from Uttarakhand, all these calamities. The first thing is, if you can actually provide communication, you can save a lot of people, lot of lives. So at this point, it's like some demonstration or some simple exercise with one base station, but the real solution that we were looking for is being able to deploy one or more base stations, flying base stations, and to provide the communication in the real world, make your telephones work or cell phones work until all the cell towers nearby are restored. So we'll look at the big picture here. The topics that to continuing the topics, we'll look into what are the technical complexities and challenges, and then ultimately, what kind of problem that you can do. If you are a researcher, what is the problem that you can address? Okay, we will stop. We'll go until that time. Yeah. So we'll go through the bullets and then pick something that requires more elaboration or more clarity. First responders means like police and firemen, including medical professionals who can help people during the critical times. So something that interesting that happened in my town is my university is in a city it's called the city of Denton. So there is a fire department, and my university and the city of Denton fire department, we collaborate, and every year we do an exercise. That exercise consists of about 100 first responders. So that includes people from hospitals or paramedics, then utilities. You remember, utility is also a big thing. If power goes, it's not that suddenly you can restore the power. We have to depend on the energy company. Then you also have to work with the community, like schools, officials, the decision makers, because you need resource. If you need a resource, you have to ask the city to give the resources. So basically, we created something called a first responder community in our city. So we all work together every year to create a scenario where we can mimic a particular disaster scenario, like this year in October or September, we are going to do something called a chemical spill. So disasters are not the same. It depends on, in case of a chemical spill, we need to figure out the challenge here is in the case of chemical spill is to figure out what are the gases that are coming out, and can you sense using sensors what is the extent of the damage or extent of the chemical spill, and then how much area we want to evacuate. So the planning starts almost 1 year ahead. So this time the exercise is in September 2025, but our planning started last year, sometime in October. So we meet once in a month and plan the things activities that we are supposed to do. Again, remember, it's an exercise, it's not a real. But the point is, if you prepare ahead what kind of things you need to do during the actual disaster, then when something happens, you can do a better job. So one thing that we are trying to do is put the chemical sensors on some sort of a fiber optic line, like some string, and then lower it from the drone, survey the area, so that we can measure what kind of gases and what are the concentrations and all that. So in addition to the communication, because when we want to deploy a base station, it helps to establish the communications or provide communication for the people. At the same time, so many other things happen during the disaster. especially medical supplies may be needed, and maybe you need to figure out how fast or how quickly you can take people from the disaster scenario to the hospitals. So, all these things have to be planned. So, point is we are working together as a team. That's the purpose of first responder community, and then we plan things like evacuation, taking people from the scene to the hospitals. So, there are other activities, not just only communications and power. We need to keep that in mind. So, that's the reason you need to have something called first responder community. All right, and as we know, each minute counts. We don't have to give any proof or anything. Every second counts during these disasters, and then the traditional communication infrastructure. When something happens like an earthquake or some other similar accident or hurricane, then the first thing is the cell towers are gone. The reason you are actually getting into this deployable communication system is to substitute, to come up with an alternative. And there are many kind of disaster scenarios, and each one is very unique. All right. So, that is the point. Why do we need aerial based systems? Because of all this. And one more thing is, remember, it's not just technology advantages. You can develop IoTs, you can design all kinds of sensors, but when disaster relief operations are taking place, somehow the technology has to fit in the circumstance. For example, the way I see is that technology should help humans to communicate better, meaning that think about like, oh, you see a victim, there is a victim and he needs some assistance. We need to be able to figure out what kind of assistance he needs, or she needs, and send it to the decision maker, so that we can provide the resources to that person. So, which means that we can't just depend on technology. Another interesting thing is, one day we developed beautiful gadget, and then I took it to the fire department. They said we are already carrying 40 pounds of weight with our suits that we are wearing. So, even you give me 1 gram is too much. So, see the misalignment. Just because we have a great idea and build a nice device doesn't mean that is going to be useful in the scenario. So, you have to be very careful in terms of what are you building, how does it fit in the situation, and is it really helpful. So in fact, my project is a combination of technology and the social science. So, we do most of or 50% of my work is to interview the first responders and see what kind of things they need, what do they do now, and what can we do, what kind of technology is needed to help them speed up this disaster relief operations. So, we have to keep that in mind. So, in general, already talked about this, but I just wanted to highlight. This is a payload. Okay, this, by the way, my student told me this picture was developed by AI. He gave some description, and this is what it developed. And I think it depicts reasonably well. So, here is a scenario, some disaster relief, some disaster scenario, potentially an earthquake or something, and then the payload is potentially it could be able to. It depends on the capability of the drone, right? So, how much you think the 5G base station can weigh? If you talk to any company like any 5G company, up to about 20 pounds, including the battery and everything, it could be up to 20 pounds. In my town, in Dallas Fort Worth, we have a company called Ericsson and Nokia. They can have the equipment, but there are a lot of configurations. It's not just okay, you have a nice system in a box and then put it on the drone. It's not like that. You have to think about the scenarios. For example, you could put only the part of the system, and maybe the core will be on the ground, and you are putting only the radio unit. So, if that happens, remember radio unit has to be connected to the core. So, how do you do that? One option is you can run a tether. That is the easiest thing to do. The reason is, if you have a tether running from the radio to the ground core, then you can also supply power. So, in one scenario, maybe potentially the more practical thing is to have a radio unit on the payload, but have connected through both power and communication to the from the ground station. That means the core unit to the radio unit could be through a fiber optic cable. So, you have to run two cables, one for the power and one. But when you do that, the advantage is you can keep the flight, you can keep the aircraft in the air in the airspace for longer time, because you are supplying the power, but then you cannot move around. That is one configuration. The second thing is, in case maybe the simplest scenario, you can just put the antennas, nothing else. You can just put the antennas on the aircraft and nothing else. All the equipment could be on the ground. But once again, you need to have the fiber thing, right? The other option is, suppose say, as I said, there is one company called Spectre Edge, which has the core also is they are built in a small form factor. So, you can put the whole thing, whole 5G base station in the air. But then, how long you can fly? Probably about 30 minutes or 40 minutes. Then what do you do? So you need to find an alternative. So, point is, there is no one form fits all. It depends on the scenario, that whether what equipment you are going to put on the air, in the air, and what equipment you put on the ground. But overall, this type of like single base station or single aerial base station has been demonstrated a lot of times, but still it is not a commodity today. When something happens, probably companies like AT&T, they are going there and then they deploy it for some time with it, like for example, if it is a tethered base station, they deploy it for several hours and then pack and come back. But what we really need is, if it is even in a rural village, in a rural area, or anywhere that something happens, we should have the ability to deploy such base stations quickly and establish. The main thing is to provide the communications rapidly and in sufficient time to be able to assist the disaster relief operations. Okay. So, these are we already covered this, like single base station and some examples. The COW stands for cells on wings. Previously, cells on wheels. So, same abbreviation, it is called cells on wheels. Some of you might have seen, cells on wheels is that you take a truck or a ground vehicle, you put a mast, some certain height, like probably 30-40 feet, and you put your base station over there. So, they are very similar, except that the configuration I talked about, like either you have to have a tether or you have to live with short duration, flight duration. Okay. So, let us go into a little more detail. These are the, if you assume this is a tethered base station, then deployment is well understood. You can work with a what you call service provider, whoever is the service provider, and you can make arrangements to deploy a base station. But of course, because it is tethered, you cannot dynamically reposition. You cannot go around. So, what does it mean? That means you have to somehow figure out where to deploy this, fix the location, and deploy it. Once you deploy, it stays for a long time because you are providing power, but then you cannot move around. And this is not suitable for a large disaster, meaning that something like, so think about it happened somewhere once in Puerto Rico. Puerto Rico is an island, and then things can happen, and like bunch of islands. So, suppose there are a bunch of islands, then one station will not be enough. Deploying one base station will not serve the purpose. Dynamic repositioning means what exactly it means, what kind of benefits you have if you are able to dynamically reposition. Meaning that, imagine that you have a infinite power and then you are able to put a base station, then you can fly around and see where people are, where people are stuck and where is the need, and then provide the communication. So, one idea that we can do, you can, everybody, each of us can think about, what kind of solution we can come up with. One idea is probably, suppose you have only one base station, one thing that can do is send a small drone, do the survey, and then figure out where people are stuck. So, remember, when you say you are looking for location where you can get maximum benefit from the base station, because deployment of a aerial base station is very costly, or more than the money, it takes time and effort. So, which means that if there is a person who immediately needs communication, then we should go there, and then maybe next from there you can go to some other place. So, that kind of dynamism is required actually. So, tether won't work. And what about battery? Today, do we have a battery that can fly, that can help a drone to be in the air for a long time? No, we don't have that. So, battery technology itself is, I am not an expert in battery. So, the point is, battery itself is a big research area, not only for disaster relief operations, but also for drone deliveries. I was praising drone deliveries few minutes ago or an hour ago, but what exactly is drone delivery is only a mile or so. It's like a luxury item. If you want a salt, or small burger or something like a pizza, do you need a drone for that? Not really. It's only, you just want to, the companies want to do it because people want it, but it's not really necessary. If you want you don't need a drone to deliver you the small things like salt and all that. But what we are talking about here is life and death scenario. Now, even few minutes, I'll also add one more, I'll give a real world example. In my city, it's called Frisco, in Dallas-Fort Worth suburb. It's a very advanced city, in the sense the city has lot of technological facilities. For example, there are traffic lights. It's very common that you see cameras. Cameras are not only for finding speeding people and all that, but it's actually, if something happens, the firemen, the fire station will actually can see through the cameras, figure out what is the need, what kind of accident it is, and what kind of resources they need. And I happen to be as a volunteer. I spent 1 week, a few days actually with the firemen, and it was so fascinating. The outcome is, whenever you make a emergency call, of course it goes to the nearest fire station or police. Especially, even though it is a fire station or firemen are coming, but actually they have the medical facilities too, right? You don't need to call a cop. Even you call a cop, it actually goes to the fire station. So, the rule is, the firemen will be ready all the time. In 90 seconds, they have to wear the uniform. The uniform is on the ground, it's like just like your, suppose I take my shirt and put it out, and like that, the suit is ready. They just jump into that. 90 seconds, they wear it. They get the uniform. They get into uniform, and in 5 minutes, they can go to the fire station, go to the accident team. So, when I was there, I think we got a call from an old lady having trouble with an oxygen. So, she needed oxygen, and by the time we went, it was only a small issue, not really a big deal. That because of the power went off, and she was not able to breathe. But by the time we went there, power came and she was all fine. That was the only real world scenario that I saw with them. But the main point is, in 5 minutes, firemen or paramedics will come to the accident scene, and probably in 15 minutes they can take to the hospital. In between, of course, they will help they have all the other equipment, other things like supplying oxygen and those kind of things. Now imagine that if we are able to send a drone, that 5 minutes can reduce to, let's say, 3 minutes, or 15-minute commute time can reduce to 10 minutes. That's a huge jump. And not only that, in rural setting, this is about urban city, right? Highly technological, advanced city. But if it is a rural area, our rough estimate is about 45 minutes for the commute. So we don't know how many people survive 45 minutes of commute time. So the biggest advantage of having a like using drones for medical deliveries, medical supplies, and the the drones again for ambulances, and this kind of application. These are the critical applications that we need. Okay, so ignore all the fun things that we can do with drones, but the most important application. This is one of the important applications. So, and then what are the benefits of single base station? Yes, you can deploy it quickly. We understand how it works. It covers one what you call some island of area. The coverage area is limited, but if you can have a better battery and if you can move around, you can do a lot. So one alternative is send one drone to look at where the people are, where people need, and then figure out which location you want to deploy the base station and do it. Isolated small areas it will work, but for it cannot. You can't expect high performance. You cannot do optimization and all those things. Yeah. And today these are common, and common in the sense you can probably, I think I talked to the AT&T person who actually was doing this work. In half an hour they can deploy. Yeah, but if it works, it works. It doesn't work, it doesn't work. But with all these cons that the negative things that we talked about can be solved with multiple base stations. So this is an example of practical cell on wings from AT&T, and this is the source. Yeah, there are many times or many scenarios or many disasters scenarios where AT&T is the only company, I believe, in the US which is doing this. Okay, and this is my project. My current project is to look into more than one base station, and look at this. If you have a coverage, if one drone can cover some area, then our goal is to extend it, to scale it to larger area. And these are, by the way, the phones. And when you put two of them, there is an interesting research problem. Again, this is for the thesis, MS thesis, or PhD students who are pursuing. The challenge is, suppose you have these two base stations. I will simplify the research problem. The simple problem is, okay, what should be the horizontal distance and vertical distance? That is the research problem we are looking at. Okay, I will give you more details if you are interested in how much should be the spacing and how much should be the horizontal and vertical. So think of like this is x1, y1, z1, this is x2, y2, z2. Our goal is to find what is the, in terms of optimization, I will give you more parameters. To begin, what should be the horizontal distance and vertical distance, and what are you trying to optimize? Remember, I mean, this most of you know, but I am just repeating. Whenever you say optimization, the question is what is that you are trying to do? What, either maximization or minimization of thing, right? So what exactly are you maximizing? That's number one. What are your input parameters? Then of course you can look into the literature or maybe textbooks and figure out, define the problem and all that, right? So when I say optimize the distance and heights, okay, the intention here is, first of all, the setting is that ignore the internet connection. You are only covering. My goal is to extend the coverage or increase the coverage to a larger area. That is my goal. Okay, let's assume for simplicity both are of the same capability, same heterogeneous, homogeneous systems, meaning that same drone, same type of equipment and all. Let's not complicate by making it heterogeneous. The next thing is, what are your resources? What are your resources here that you want to optimize? Power, right? So, for example, you can say P1 is the power, P2 is the power for this, right? And what is the output that you are trying to, what is the performance indicator, how much area you are going to cover, and then quality of service, maybe how many users you want to provide service. These are the things, right? How many users, how many phones will work. That depends on how much bandwidth you have. So I think we were talking about this just few minutes ago. So bandwidth is like a real estate. Somebody told me it's more like a yeah. I think you can come out with some other examples, but basically it's like a real estate. The more bandwidth you have, the more users you can service, and more quality you can provide, and all that, right? So very clearly, let's assume this is P1, power is P1, and this is for P2, and then for simplicity's sake, let's assume we are putting in the same straight line. So meaning that let's fix the horizontal. Fix the height, fix the altitude. Then you only have to deal with one parameter. What is that parameter? How much should be the distance between them? And again, remember, you are optimizing whenever you have optimization problem, one simple idea is fix everything and focus on only one parameter that you need to solve. So in that sense, let's say this is P1 and P2 is fixed, and the distance is the one you want to find out. That means you also fix the altitude, and then our goal is to minimize the interference. That's the key thing. So where is interference coming from? Now, of course, if you have a nice framework where you are providing, you have some sort of a scheduling in terms of time or frequency, that's a different issue. But here, a simple scenario is like you can assume that they are both using the same frequency. No, you are not. There are no allocation at this point. Simple. You are putting two stations in the air, two base stations in the air. You want to minimize the interference, but at the same time you want to increase the coverage. Or you can put one of them. You don't, maybe putting everything is a challenging thing. You can say you want to increase the coverage area. What do you mean by coverage area? You need to again go deeper. It means that suppose this is the outside ring. When you say I am able to cover this much area, what does it mean? That probably at the edge, your the receive power is above the sensitivity level of the radio. For example, then you can say minus 90 dBm or minus 100 or minus 90, whatever you choose. You are making sure that the longest distance is where your receive power is above the threshold. So typically when we solve optimization problems, you will fix everything and start on having only one variable that you want to find out or find the value. I think I explained enough, but I will show you some reference papers. That way you can really see somebody is actually solving a problem that is similar, by the way. So once again, what happens is when you want to, whatever problem I said, okay, how do you deploy two base stations in optimal heights or optimal distances and maximize your performance? That is the problem. But one thing is, if you look in the literature, you will find something similar. You may not get, if you find exactly the same thing, probably it won't be new, or maybe you can say that's not the end of the thing. Even somebody has actually solved the problem. If you look carefully, you will see, oh, they missed something. So don't be discouraged. I don't really believe in that. If we have come up with a nice solution, oh, somebody has done this. That never happens. It happens that somebody had worked on it from a different angle. Okay? So you should never assume that, oh, I worked so hard, and then after 2-3 years, what if somebody else done? Because you worked so hard, even exactly same thing happened done by a digital twin of yours, but I am sure you will find a new twist to your problem. In fact, it happened to me, for one small problem. I was working on some other subject topic, but I don't want to deviate it deviate from the context now. The point is, there is a problem that I gave it to my students. I'll show you. This guy, yeah, I think. Yeah, these are some of the references, but there was one problem that I found where the researchers were trying to optimize the placement of one base station, one aerial base station, with respect to a ground station. So there is a terrestrial base station and a ground and aerial base station. They are trying to optimize the placement of the aerial base station with reference to the ground base station. That means existing cell tower. Okay. Then let's continue. I hope you see the main idea here. Let's go back to. So we were here. Not this. One more second. Yeah, so anyway, this is the problem, right? So the problem that I found in the literature is, if you replace this ABS with a ground based terrestrial cell tower, and then with reference to that, how do you minimize the interference? So look at one more second. Let's spend one more minute on the interference aspect. So if there is a user here, this person is getting information from this as well as this. So if you refer to the user getting service from this base station, so whatever is coming from this base station will be interference. Of course, you can argue that, oh, why can't we combine them? That's more challenging. You can, even though if you are getting service from both base stations, combining them constructively for increasing the quality is more complicated, because we are not looking into that. So basically, you want to provide, you are thinking the user is getting the service from the one base station, the other signal will be a strong interference, will be interference actually. Yeah, I hope you see the main idea of what is the research problem here. Okay, and as I said, there is a problem that has been solved in other context, where one is the aerial base station, other is the terrestrial base station. Okay, with respect to multiple ABS station, so what are the benefit is increase the coverage area. Then if you more than two is more complicated, but I think the problem of two base stations itself is not really understood. So if you are able to define a problem and solve it, that will be a good contribution. And of course, if you have more, as I said, practically I haven't seen anybody deploying more than one. And in terms of research, there is work done in terms of even multiple base stations, more than two. Placement of aerial base stations is a good topic. And what do you do over there? Resource optimization. Now, what are the resources? How do you handle how do you manage the bandwidth? How much power? All these are power and bandwidth in communication system, really speaking, those are the two resources that you have to work on. And then come up with a good notation, give the variables and figure out exactly what you are trying to optimize. Simplify the optimization problem by focusing only on one variable, and that will be a good PhD for that. Okay. Then the other thing is, yeah, good. I'm able to figure out now how to go back. So this second station doesn't have to be another base station. It could be a relay. Why relay is important? Again, you can just all you need is putting some SDR, maybe a software defined radio, that acts like a relay from this user data, goes through this and then goes to a base station. So suppose you have somewhere here you have a cell tower. Our goal is to be able to provide communication among the users within the area, but from here you should be able to make an internet call and connect to the old internet or rest of the internet. So that is called in some term, in some term it's called also backhaul. Backhaul means internet, basically think about like internet connection, and now you can imagine how many ways you can come up with this internet connection. One is, yeah, if this base station or a relay can connect to another cell tower, you are good. The other option is maybe you can use a satellite. So for backhaul, again think about backhaul as a connection to the internet, because if you are able to provide one, if you deploy one base station, it provides coverage for certain area, and that's it. So why do we need it? Suppose the first responders are here, they are able to communicate, or if or maybe one person can call other person within this area, but it doesn't mean that you are able to make a call to somebody else outside this area. So for that you need a backhaul. Backhaul could be through the relay. That's one option. The other option is maybe through a satellite. So these are all options, but there are challenges with each of them. For example, if you think about geo satellite, the delay is longer. That probably takes longer time. But then other option is LEO. With LEO satellites, we all know that the satellites only stay for a few minutes in the horizon and then they go away. So then the challenge is about handing over. But in general, for example, if you buy the SpaceX terminal, you can use that as a backhaul. Starlink thing, it works actually, Starlink. Yeah, in the context of LEO satellites, there is one more research project that I am currently involved, is that how to predict the satellite. So that's something quite interesting. Let's say, of course, satellites are predictable, but what we are looking for is not just a prediction of a particular satellite. The challenge here for us is, I'm actually going away from this context. Suppose you are making a phone call, you are connected to one satellite. I'm making a phone call and connect to a satellite. So if you are able to predict which satellite comes next, then you can do the handover quickly. Otherwise, what happens? Your phone has to see, which satellite is going to come, based on just like the way we in cell towers mobility management is handled. We can, depending on your mobility, your phone will tell you which cell tower to connect to. But here what we are saying, which satellite to connect to. But obviously it is more complex or more time consuming. If you are able to predict which satellite is going to come next, then probably you can be like a proactively connect to the next satellite, right? And that's not enough. You need to think about what next. Because if your phone call lasts for 30 minutes, you are going to connect to multiple satellites. So understanding or predicting the sequence of constellation of satellites is a problem that we are working on. And again, I haven't done a thorough literature survey on that. There are works by other people. I'm just sharing with you in terms of the challenges associated with the satellite connection. But in general, satellite connection is a good backhaul that you can think about. And one more thing. Let's assume this is for a minute. Let's assume this is our terrestrial tower, okay? And I want to see, again, our goal is to connect a backhaul. So to do that, there is something called in-band communication. Some of you again may be familiar. What do you mean by in-band communication? Within the bandwidth that is available, or within the spectrum that is available for this base station, you could use most of it for connecting with the grounds, and a percentage of, let's say 20%, to connect as a backhaul. So basically, in in-band communication, you are using 20% or some percentage for backhaul, and the remaining is for the users. So that's also a beautiful, if you type, go to Google and type example of in-band communication, you will see some examples. In fact, when I was sitting with my student, I wanted to give him an example. Then I actually asked for a I went to ChatGPT and asked for, give me a numerical problem for in-band communication. It gave a beautiful problem. So they actually gave numbers. So remember, sometimes we say bandwidth and all that, unless if I ask you, oh, give me a number for bandwidth, you may be able to give, but it's not, it may not be practical. Suppose you say, oh, 1 gigahertz. It may be, if you say it may be too high basically, or if you give me an example like, oh, 10 megahertz may be too small. So by taking a real world example, you will appreciate how to define a problem properly and also solve it. So in this case, roughly a typical scenario for a base station is, let's say your bandwidth is 100 megahertz. So the saying is 20 megahertz go to in band as for backhaul, and 80 megahertz is for providing the service. So you can compute now. So suddenly the problem become more practical. Say how many users you can provide, and of course you have to ask more details, or what kind of services they are using. If it is only for phone calls, probably 5 megahertz is good enough for phone call. But if they are using something more like, of course, in emergency scenarios, nobody will watch TV and entertainment. So with some assumptions and more realistic values, you can solve a real world problem. Okay? And these are all open problems, by the way. It's not that with base stations, each problem that I just talked about, at least if some parts might have been addressed in the literature, but there are many open problems. And in fact, as I told you, right, my student told me after his research said, nobody deployed more than one base station so far in the world. That's what about backhaul? No rigorous backhaul. I think I saw, long time back actually, many years ago, there was a satellite station. There's a big van with a satellite connection like a SpaceX terminal, and then here you are deploying. Only for no, it works, but it doesn't really. It's not solid. And by the way, there is. Lately, there is so much emphasis on resiliency. In fact, I was sitting in a panel one of these recently, and there was a beautiful, well-written proposal by someone who really understood what resiliency means. And I can't give you more details because I'm not supposed to tell. The point is, that caught attention. Resiliency is so critical. In fact, I have another project from National Science Foundation. It's called Resilience Intelligent Next Generation Systems. It's abbreviated RINGS. There was about $1 million grant. I'm fortunate to be selected among the 40 applicants, 40 proposals that were selected by National Science Foundation. Mine was one of them. It has been 3 years, but a lot of wonderful work has been done in that. So resiliency means, given the uncertainties, given the challenges, can you keep the network live? Can you keep the connection live? That's important. Think about when somebody, in this scenario, somebody is making a 911 call. Don't you want that connection to be resilient? Okay, so that is the power of this. That is the reason why I was passionate about this project. Since 2016, I've been working on this. As I said, first I got a small grant and I was able to demonstrate, but it's not. I'm not happy, because what's the big deal? You show something okay, here is a drone, here is my, I'm able to make a phone call. It doesn't mean anything. What we need is, can you deploy such systems on demand in 20 minutes or 30 minutes and make sure that the connections are resilient? Then you make a case. Save one person. That's it. Whole life you can be happy. Maybe you can get a ticket to heaven, Anyway, I think let's stop here, and then we'll talk more in the afternoon. Okay? I think this is my first lecture. I hope the way I wanted to present to give you a big picture. Why this problem is important. As somebody said, who cares? That's number one. Number two is, if you are a researcher, what is it for me? What is it for you? What is a small problem that you can take, do it like a part of your MS thesis or a PhD topic, dissertation. And there is enough information for a PhD topic here. In fact, I have one PhD student already in the middle of this. And because of this grant, I am able to support one more student who just started. And then yes, actually I can provide, I'm actually looking for another PhD student who can work not only in this, but in related topics. Okay. So, I think I hope the purpose is served. I hope that you see the value of this kind of work. Okay. All right, let's stop here. Say again, which?